Isobath. In this exercise, we have a robot described by the following state equation, and x, y, and z corresponds to the position, and psi corresponds to the heading angle. We know the initial condition given here, and we also know the seafloor, which is described here by this equation. The robot is able to measure its altitude. It means the distance to the seafloor, and also the gradient of the seafloor just at the place where the robot is. So I will try to explain this now. I have the space which is described here, and the robot is below the water, so z is negative below and z is positive above. Since we have an underwater robot, we are below, so I will try to represent the robot here. And the robot is equipped with some sonars. So the sonar will able to see what happened below. It is oriented below. So it's difficult to represent here, but I have an idea of the seafloor, like this, for instance. Three-dimensional, like this. So as we can see, just below there is a sonar, like this. So is able to send some waves, and from the wave it is able to have an idea of the plane which is tangent to the seafloor. So this corresponds to the plane. So it means that we have an idea of the altitude, so it corresponds to the altitude, but also of the gradient of the seafloor. So the gradient is corresponds to this vector here. To the gradient of the seafloor, it means direction where the seafloor goes up. So the robot is able to measure its altitude, the gradient of the seafloor, but is also equipped with a pressure sensor, and from this pressure sensor, it is able to get its depth. It means the distance to the surface of the water. So the depth corresponds to this distance here, and here we have the surface of the water at altitude z equal to 0, of course. So the altitude is positive. For the simulation, we will assume that we know the seafloor, which will be described by this equation. To have a better idea, I will represent a two-dimensional view. I have here the surface of the water, z equal to 0. Z is oriented like this. The robot is under the water. It is able to see just at the direction of the sea bottom. The sea bottom is represented here. We'll know the equation only for the simulation, but of course the robot does not know anything. It will be able to measure using a sensor, a pressure sensor, the depth, which corresponds to y3. It is able also to measure the distance to the seafloor, which is here, so the vertical distance, which corresponds to y1, but also it is able to know the gradient. So it means for two-dimensional, the slope, which represented here. So in a two-dimensional view, the bottom will be like this, of course, something like this. Difficult to represent. But I will have some level curve. This level curve corresponds to, for instance, z equal minus 15. Here, z equal minus 14. Here, z equal to minus 16, for instance. And what is represented here? It is called, so here, this curve, maybe like this, this curve corresponds to an isobath. So the depth is constant and corresponds, this one, to minus 15 meters. So the gradient, if I try to represent the gradient, it will be a vector corresponding to the direction where the slope increases as much as possible. So here, probably something like this. And if you want, I represent a two-dimensional view of the gradient of h of xy. And here it will be h of xy. And the robot is located at xy, and here z for the robot is negative. So we can see from this relation that if I call, so h at this point corresponds to this, it will be h. So what I can see here is that h, which is here negative, so oriented downward, plus the y1, which corresponds to a distance, so it will be positive, oriented upward. So plus y1 using the sonar, so sonar, plus the pressure will give me the depth, y3, equal to 0. So this is measured, this is measured. If I now see from above, I will have here my level curve. So here, for instance, z corresponds to minus 15. So level curve like this. So minus 16, minus 14, no, 17. And if the robot is here, we can see that the gradient in this situation is oriented in this direction. And the robot will be able to see that on the left it will increase. Indeed, it will increase, since here I will have v equal minus 14. So this is the gradient, and the robot has a heading which corresponds to psi. And what is explained here is that the robot is able to measure the angle of the gradient, so this angle, in its own frame. So it means that it is able to see this angle, and this angle corresponds to y2. So recall that the robot is not able to know its position x and y. He has no compass, so he is not able to know its heading. He only measures its depth with respect to this, the distance to the floor, the vertical distance y1, and the direction of the gradient in its own frame. That's why the controller u will be a function of y1, y2 y3, and we will not be allowed to use x, y, psi, which are not known by the robot. I will start with this simple program, Python program. In this program, I show the C bottom represented here. I can see the robot in blue. I have here the shadow at the surface of the water in gray, and black it is the shadow of the robot, the AUV, at the seafloor. So the robot is able to measure this distance, has an idea of the plane or of the gradient oriented here like this, and from this it will have to follow an isobath. So it will turn around this that could be an island. Okay. So first I will use roblib, which contains all functions we use for this MOOC. Okay. I have here the equation of the seafloor. I use only for the simulation, but the robot does not know, has no idea of the seafloor. So I will use mesh grid to build the mesh. So between minus L and plus L, which corresponds to 10 meters. L corresponds to 10 meters. Here I have plotted the surface, but so I have a three-dimensional view of this, and also I have drawn the AUV. So AUV, autonomous underwater vehicle, 3 dimensions. So all these functions to draw AUV are given in roblib here. Okay, which contains all we use here. The mod draw AUV is here. Okay. Okay. So we use twice draw AUV just to draw the blue one and the black one corresponding to the shadow. If I want to see the contour instead of the surface, here I write contour, and I will see the isobath. So isobath as represented here, and we can see here two. Okay, the level curves are not totally convex. The isobath are not totally convex. We have this shape represented here, and you can see that isobath are not necessarily connected, as we can see with two yellow isobath. Okay, the explanation of this shape is clearly given by this equation. We can see that we have the sum of two Gaussian. The first one is centered in -2, -2, and the second one is +2, +2, and it explains why we have this shape. We can see that when we are far to 0, then h corresponds to -10, which means that almost everywhere the depth of the seafloor is something like -10 meters. Okay, now if I come back, I will try to simulate the robot. So I need to write first the evolution function, which is given, the evolution function is given by the state equation, and I will have to simulate this. So first I will do a for loop. So for t equal or in a range. So I will start at 0, for instance, that will go at 5, and with dt. So dt is a small number. So I will write, for instance, dt equals 0.05. Here I will use the Euler formula, which tell me that the new state corresponds to the old one plus dt times f of x and u. So I did not I need to define what is u, which corresponds to the input. So at the beginning I can put u equal array of, so I will write to start 0 0 0 0. Here I will draw the AUV. Draw the AUV x, and of course I will have to remove this one to put the draw mesh, for instance, here, otherwise it will. And also I will have to in draw to erase the old one, so CLA like this. The pause I will put it after the program, otherwise he will remove immediately the picture. I will put a small pause to let the computer draw the picture, so for instance something very small, otherwise it will draw everything only at the end. Contour I will replace by plot surface, and I am able here to see the simulation. So of course u equal to 0, but we can see the AUV moving. I have now to build a controller of the form u, which is a function of y1, y2, y3, what I measure, which makes the robot follows an isobath corresponding to -9 meters, but at a depth of 2 meters. So I will first build the controller for the depth, which is easier. So u1, which moves z, so which have an influence of z, the depth, I will start by u1. So I have here the surface of the water, which corresponds to z equals 0. And I have my AUV, which is, for instance, here. At the depth y3, which may correspond, for instance, to 3 meters, which is positive, so oriented upward, z. And I assume that I want to go, for instance, here, for the robot, for instance, at the depth y3, which corresponds to 2 meters. So in this situation, I will have the error y3 minus y3 bar, which corresponds to, in this case, 3 minus 2, which is equal to 1, which is positive. And in this situation, I have to go upward. So it means that I want to move to have u1 positive, and I will try, for instance, u1 equal to this. But I could take another gain, for instance, k y3 minus y3 bar, as soon as k is positive. So if I want to go fast toward the desired depth, then if I want to go fast, then of course I will have to have k, which is large. So I will try to program this now. So I have added in the program J, which returns here uh, uh, an array. The first part of the array corresponds to y1. Here I have y2 and y3, and they are given by the equation that are in the exercise. So y1, y2, y3. And for the gradient, I used a different. I use a method with finite differences, which so I compute the gradient of h like this. I take a small, very small, so here it's not so small, but zero 0.1, consider as small. I move on the with respect to x, I make the difference. So I obtain the derivative with respect to x. And here I do the same with y, so I obtain the derivative with respect to y. And I have an approximation of the gradient. The gradient is used here. And I obtain a vector. This vector has an angle which computed by the angle function which is given in roblib. And I will remove psi corresponding to the heading. Okay. So now it is not finished. I have to, in the program, in the simulation, to take y equal to j of x. So it is what I measure. And the control, u, equal to control of x. Okay, I'm not allowed to use y. So I will have to define a control function, for instance here, def control of y. I will flatten y to make the use of the substrate easier. I will return an array corresponding to the control. So u1 will be given as a first component here, u1, here u2. So at the beginning I will not take care about the heading later. And for the u1 I will it is given by y3 minus y3 bar. So I will since I have to go to a depth of 2 meters, I will consider here y2, which corresponds to y3, because in Python we start the subscript at 0. So minus 2. And here I have the coefficient k. I can put what I want. If I want to go slowly, I will put, for instance, 0.1. Here you have to return an array. I don't need these parentheses. Okay. I run this. And we can see that the robot goes from 0 to -2. So slowly, probably too slow. So if I want to go faster, and with another, for instance, if I want to go faster, I will change the control. And here I will write, for instance, 0.5. I will go faster. And if I want to go to a depth of 5 meters, I will write -5. Check. Okay, I go faster. And I go to -5. slowly. Okay. Now, because the error is small. Okay. Now we have to tune U2 corresponding to the head control, where we have to follow an isobath. Oh, I consider first some isobath. The first one, for instance, the one where we want to go, let's say minus 9 meters. Another one, and so on. So for instance here, minus 8 meters, minus 7, minus 10, minus 11. Assume that our AUV is like this. So it is going in the right direction, and we'll ask first the AUV to go to follow an isobath. Of course, we want to go along this isobath, but first at the beginning we will try to follow the isobath where we are. Okay, so we'll consider some kind of error. So assume that I am able to measure the gradient. So the gradient, if I write the gradient will be like this here, like this here, like this here, like this here. So here I am following an isobath in this picture, and we can see that the angle between psi, so my angle, and the gradient corresponds to something like pi minus 2. Okay. If I am like this, the gradient will correspond to so I will see, the robot will see the gradient on his left, whereas it will be here on the right. And if I am not following an isobath, so I will try to show a configuration here, I will see the gradient not exactly at an angle of p divided by 2, but something which will be different. And in this case, I will have to correct it. So this error, I will code it E1, and it will correspond to Y2 more or less p divided by 2, because I want to see either p divided by 2 or minus. So here, for instance, I will consider, I will take plus. Okay, I could have taken minus also. So if E1 is equal to 0, it means that I am in this situation, which is a good one. I follow an isobath. Maybe not the right one, but I see I follow an isobath. And because it is an angle, and I don't want to have the plus 2 pi problem, I will filter this one by the sawtooth function. So I will take, for instance, as a beginning to start to follow I will take U2 as sawtooth, the sawtooth function for angle of y2 plus p divided by 2. Okay. Now, if I'm not on the right isobath, I will have to correct it. For instance, if I am in this situation, I'm not on isobath, so I will move the direction where I am going, where I want to go, so this one. I will change on the right or on the left, depending on the difference between the isobath where I am and the isobath where I want to go. So this error, I will call it U2. So I had E1, now U2. This error corresponds to Y3 plus Y1 plus h0, where h0 corresponds to the one where I want to go. So let me explain this. I have here the surface of the water. I have here my robot, AUV. I have here in the positive direction y3. I have here the seafloor. I have y1 corresponding to this, so the altitude, which is positive. I have here the isobath where I want to go. So here it corresponds to h0, which is for my exercise minus 9 meters, which is negative. And here I will have the error. I will call it E2. Okay, so it is clear that the sum of all of them is equal to 0. It means that the second error, E2, is equal to minus y1 minus y3 minus h0, and I want this error to be also equal to 0. So for u2, I will write here the sawtooth function for to have the right to follow an isobath, and here I put the error E2, but I also add a saturation function, hyperbolic tangent, to avoid to have this error being too large and having a strong influence on the input. So I will have this moderation thanks to the saturation function. So I add h0, which is the one we want. So h0 corresponds to minus 9 meters in the exercise. And it's done here. So my AUV goes to the right depth and will follow the isobath like this. So probably I will take more time, and also probably it was not the right depth. Control it was 2 meters, which was required by the exercise. I will take here, go faster for the simulation, and I will put something like 20 to have a longer simulation. Okay. So I follow the isobath, and probably if this corresponds to islands, I will be able to turn around the islands without any perception of the environment except what I have just below, just under the robot. So a last remark for our AUV. What we measure here is y1, y2, y3, and for the heading, for the control of the heading, we use the control we have just explained before, but classical controls that could have been used also, in which is very similar, is proportional and derivative control. So in this case, since I want to have y1, so y1 which corresponds y1 which corresponds to z minus h of x and y. We want the one we want. For if I want to control this one, I want this one to be equal to y1 bar. It corresponds to y3 minus h0. Okay, this one corresponds to the pressure sensor. So in our case, it was controlled to, okay, I could bar here to -2. So because the depth is 2 meters, plus 9, because this one was equal to -9 in our example, and here it corresponds to 7. So what I want is to have this one equal to 7. So a classical proportional and derivative control tells me that what I could take is y1 bar minus y1, so plus a coefficient, but I don't write it, plus the derivative, y1 bar. And this one, I use this, and I know that it is z dot minus gradient of h of x and y multiply by x dot y dot, and x dot y dot are given here cos psi sine psi. Okay, the problem to implement this proportional and derivative control is that this one, okay, I can assume that this one is equal to 0. Okay, otherwise I can get it from u1. And this one is unknown because I don't know the heading, and I don't know this. Okay, but this can be approximated, and it is what we have done here, by sawtooth. Not exactly the same, but very similar, by sawtooth of y2 plus p divided by 2. Okay. So in fact, what we have done in this exercise is very similar to a very classical proportional and derivative control.